Hi there. So we're going to look at a certain subset of different types of partitions and equivalence classes that are going to be, not showing up in every single problem, but are a nice, helpful way to continue to think about those ideas. So get yourself ready for notes. We're going to talk about integers in modulo. So we're going to be talking about something called modular algebra, which we've talked about a little bit before. But we're going to add in some vocabulary here. And so the way that I want to start is that this is always going to be written as the integer sign with a subscript n. So integers in modulo n, you just want to look at what that subscript is. And what this does is divides the integers into a partition based on the equivalence classes in modulo algebra. So 0, 1, 2, all the way out to n minus 1 by the equivalence relation, equivalence in mod n. So it's just an idea of like how to partition up the integers and think about them as, okay, what would they be in mod n? One of the reasons that this is helpful is that we can do something called addition and multiplication tables. And we're going to start by looking at the integers mod 3. So we've looked at this equivalence relation before. And here, the nice rule here is if we add them together, we actually don't need to necessarily think about what the number would be in this set, but we can think about how any number in any of these equivalence classes would behave. And so what I mean by that is that if I have any x in an equivalence class A and y in the equivalence class B, if I want to know where x plus y is, well, that's in the equivalence class of A plus B. And this is the same for addition and multiplication. So not subtraction and division, but works just fine like this. So if I have a number in the equivalence class of 0, when I add that together, it's going to stay in 0. 0 plus 1, 0 plus 2. Now here, this is 1 plus 0. Here it's 1 plus 1. Here, 2 plus 1 is 3, which we will rewrite in modular algebra as 0. So here, you want to make sure that as you come full circle, you are converting back as need be. 2 plus 0 is 2. Here again, we have 2 plus 1, which is 3, so it is the equivalence class of 0. 2 plus 2 is 4, which is in the equivalence class 1. As I said, same thing is true for multiplication. 0 times 0, 0 times 1, 0 times 2. All of these are going to stay in the equivalence class of 0. Same with this column here. 1 times 1 is 1. 1 times 2. 2 times 1 is 2. Here, 2 times 2 is 4, which is in the equivalence class of 1. Now, for in mod 3, find the equivalence class of 7 times something in the equivalence class of 8. So you can either convert them first. So there's two strategies. Either you can say that 7 is in the equivalence class 1 and 8 is in the equivalence class of 2. So then 7 times 8 will be in the same set as 1 times 2, which is 2. The other strategy that you can do is just say, well, that's going to be in 7 times 8, which is 56. And then you ask, what is 56 in modulo 3? These are definitely things you can do. 56 is 3 times 18 plus 2. Sometimes it's just easier with long division. 2 is the remainder, so we're looking here to say that that is in the equivalence class of 2. Now, of course, I've been using this fact. We would want to prove that it's true. So we're going to prove it true for multiplication here. So what I'm going to do first is I'm going to say that the equivalence class A is equal to, and I'm just going to call this A prime, where A prime is in that first set here from 0 to n minus 1 of the different remainders. So 0, 1, 2, and so on, out to n minus 1. Similarly, I'm going to say that B is the same as the equivalence class of B prime, where B prime is in that set. So what that means is that A is equal to n times x plus A prime, and B is equal to ny plus B prime. So this is just the definition in mod n. It's a multiple of n plus the remainder. Now I want to worry about A times B, so I'm going to say AB is equal to nx plus A prime times ny plus B prime. Now when you FOIL that out, you get n squared xy plus nxb prime plus ny A prime plus A prime B prime. Factor out n from the first three terms, which you can do, making that a multiple of n, y A prime, B prime. So I'm going to say, since all of these terms, x, y, are all in the integers, so by closure, this is equal to an integer I'm going to call z. So therefore, AB is equal to nz plus A prime B prime, which means that AB is in the equivalence class A prime B prime. Therefore, if I take AB times B, then that would be equal to A prime times B prime, which is equal to A prime B prime, which, as we can see right here, is in the equivalent, has the same equivalence class as AB. So here's a nice use of equivalence classes and partitions. Please let me know if you have any questions, and have an absolutely wonderful break.